like to welcome all of you in the audience for attending this lecture. As mentioned, in short, I'm going to talk about some of our capabilities for space communication and some of the challenges associated with that, as well as some of the new technologies we're developing to meet those challenges. And it's quite an honor to be here and speak with you here today. So from the very beginning, one of the most fundamental reasons that we endeavor to go to space is for information. Information finding and of course delivering that information back to Earth, and space communications is the conduit for the delivery of that information. Information comes in many different forms, and one of the most common forms that is relatable would be in the form of pictures and video from throughout the solar system. So I'd like to start this presentation by sharing with you some of my favorite images from around our solar system. In the NASA archive of all the images, this is my favorite. This is an actual image taken from the Cassini spacecraft. It's actually a retake of an original image, and this image is a beautifully backlit Saturn. You can see the sun directly behind and the beautiful shadows of the moon. It was taken in 2013, called The Day the Earth Smiled. So on that very day, we were all supposed to look up and smile because we were getting our selfie taken from Cassini. So certainly it's a very gorgeous image, but an image like this also contains important scientific information, such as if you take a look at the rings of Saturn, they appear to extend out very far in diameter, and you see that milky white ring all the way on the outside, which is in fact the trace of the orbit of one of the many moons of Saturn, Enceladus, which has some saltwater jets in the South Pole, which is injecting salt water, tracing out its path. So it kind of looks like an extension of the rings, but it's actually the path of Enceladus, which is something that we wouldn't be able to discern from a ground-based telescope. So the ability to navigate and communicate successfully at Jovian distances out to a planet such as Saturn allows us to gain some very fundamental insight into that activity and that particular planet, which we hope to land on sometime in the near future. We've got several mission concepts taking a look at landing on Enceladus. All of us are in this picture. You can see us very humbly in the top left-hand corner as we gaze up, smiling as our selfie was taken. And if you're wondering, just kind of from a very top-level view, what NASA's doing and why they're doing it, every single piece of resource allocated from Congress to NASA throughout the NASA space programs are trying to answer one of the questions that you see here on the screen. Our whole our heliophysics portion of the science mission is trying to study the sun, right? The origins of the sun, the current state of the sun, the future of the sun. We've got planetary science, we've got astronomy. So everything basically hinges on these very simple, seemingly simple, but deep questions that we're trying to answer about our solar system and our greater universe. And every mission that we launch and every picture and piece of data and telemetry that we get back is ultimately trying to answer one of those questions that you see here. This journey has been going on for well over half of a century now, and to date, this is an interesting map of everywhere where we've been in our solar system. And I wanted to emphasize the importance of your and my time right now existing during this journey, because you can consider just a couple generations ago, we had not visited any of these other worlds. And now we've visited every planet in our solar system, and even several of the moons of several of those planets in our solar system through all these missions that you see here on this chart. So now every time that we go out with a new mission, we'll be returning to these same locations, gathering more data with increased instrumentation capability, increased imaging capability, and all this happened within the time span of a single lifetime, which is amazing when you think about the fact of how many centuries we've been here as humans and never had access to our home, which is the solar system, until now. Okay, this journey really started in terms of sending images back with a satellite called TIROS-1 in 1960. TIROS was an interesting partnership between the NOAA agency as well as NASA, and we still have this important relationship today. NASA actually designs and operates the weather satellites for NOAA, and this was the first of its kind. And so what you're seeing is the first live televised image of Earth from space. Crude as it was, it offered the higher ground perspective and is very humbling, and really began the whole campaign of space weather observation. Now we take that for granted, that we can always see clouds and predict hurricanes based on space weather satellites. But TIROS was the first time that you could turn on your television set and take a look at a live analog image broadcast from space. We've certainly journeyed to the center of our solar system, the very center, the sun itself. Those are our heliophysics missions, which I had mentioned. There's an interesting space app that you can download to your phone called NASA Space Weather, which tells you the weather of the sun today. We have several missions observing space weather. One of them is called Stereo. Stereo is a very interesting mission where it's two spacecraft that are in orbit around the sun. And we take the images of both and composite them together so that we have 3D pictures as well as video from the sun. They've completely gone around it. So nowadays you can actually buy a solar globe with the entire surface mapped. If you go on Stereo's website, you can view the video with 3D glasses. If you don't have 3D glasses, you can just view one of the Stereo spacecraft. But I'll play you a quick little video of Stereo, and there's many up there again on the website. So here you can see some of the solar flare activity peeling off the surface of the sun, and with that solar flare activity comes a few things. A lot of radiation gets ejected, coronal mass ejections peel off the surface of the sun, and some of that can be very damaging to our lives back here on Earth. So just to kind of hammer in some concepts here of space communications, considering a mission like Stereo. So when one of those solar flare activities happen on the surface of the sun is about a fixed distance away from the Earth, and we call that distance 1 astronomical unit. It's basically about 150 million kilometers. And when you look up at the sun, the light coming from the sun takes a period of time to reach your eye. So you're always seeing the sun the duration of time ago, right? You're seeing what the sun used to look like, specifically 8 minutes ago. Same thing with the solar flare activity. If a solar flare were to happen at the sun and we had a telescope back at Earth, it would take 8 minutes for the light of that solar flare to reach the Earth. Now, Stereo is in orbit around the sun, the two spacecraft, Stereo A and Stereo B. So they're taking observations of the solar activity, and they're going to then transmit those images all the way back to Earth, and they're going to use radio frequency communications to do so. The rules of the road are, because RF is in the same electromagnetic domain as light, it's governed by the speed of light. And so the signal from Stereo also takes 8 minutes to reach Earth. Okay, so Stereo will see a large solar flare activity, take a picture, take a composite of pictures to make a video, and then sends it off to Earth to say, hey, look at this. Now, we would like to know this because we've got astronauts and cosmonauts on board the International Space Station, and that solar activity could be very hazardous, could even be lethal to them in orbit. The actual material, the coronal mass ejections coming off the sun, we call these CMEs, take much, much longer to reach Earth. So the message comes from Stereo that we have a large solar activity event, and we get that information, and if it's severe enough in magnitude and direction that we think it's possibly going to intercept Earth and, let's say, the International Space Station or future habitats on the Moon, then we would instruct the cosmonauts and the astronauts to take some shelter. Typically, where the water is stored, because water is an excellent insulator, absorber of radiation. So those ejections, they can take a few days. It's about the speed of what we call a solar wind, which is a supersonic velocity, fast but much slower than the speed of light. Right? So it takes some time for the coronal mass ejection to get all the way to the Earth, and it can be very harmful. It can knock out our cell phone reception, and any type of RF-based reception around the Earth. Can cause hiccups in electronics, and of course, if you're out in space, not shielded by our upper atmosphere, can be lethal. Now, of course, us protected within the veil of our atmosphere, we enjoy this type of activity, especially if you live in the northern climates. I'm up in Cleveland, Ohio, so when there's great solar activity, then what happens is that solar activity will interact with the upper atmosphere from the North Pole, and on high periods of activity, the aurora borealis will grow larger, the ring will grow larger, and thus come down latitude. And so at the 5 o'clock news, if they happen to say that tonight there'll be a larger northern light activity. How do they know that? Well, because we know that we have some solar flares and the timing is such reaching Earth. So it's a very pretty event if you're protected, with our Earth's atmosphere. Okay, but that said, if we're going to have a Martian habitat or a lunar habitat, we need to depend on those heliophysics missions like STEREO and the others that we have to continue to monitor this activity so that our explorers can take shelter. Another great way to take shelter if you're on the Moon or in Mars is to go inside a cave. Go underneath the lunar regolith would be excellent protection. Okay, we've journeyed very far out in our solar system, but starting in the other direction, just going out to Mars. We've also observed the sun. We've even taken video of sunsets from Mars. I have a video of that here. So here is a video of what it would look like watching the sunset from Mars. You notice how small the sun is because you're that much further away from it. And the sun's going to duck behind the hills of Mars here. This is taken from one of our rovers. Very quickly you notice not only the sun smaller, but it's blue. And of course that's because the Martian atmosphere is made up compositionally very different than the Earth's atmosphere. So the refraction of light is different. And although it's the red planet, you get blue sunsets. Very interesting. So you can go tell your family after this that you've watched a sunset from the hills of Mars. I wanted to show you some video here that we have from the landing on the surface of Mars with our latest rover. We're about to get our next one, large one out there, but this was the Curiosity landing. So this was the entry, descent, and landing phase. You're looking at the downward-facing camera on Curiosity. You're looking down on a mountain range. Particularly that range is called Mount Sharp. And this was a great engineering accomplishment. You can see how we're kind of nutating around on descent. There's a bridle and reaction rockets slowing up the ascent. And when we get very near the Martian surface, you'll see the wheel deploy and the kicking up of the dust and finally touchdown. Now, this video we were not able to watch live because, again, of the speed of light. So Mars is very far away from the Earth. It's a variable distance depending upon where you are. When Mars is close, it's typically 0.4 astronomical units. When it's very far, it's 2.7. What that translates to is the time delay could be about 4 minutes up to about 20 minutes of delay. So the video comes very late. And it also arrives very slowly. Our communication rate to send those images is much slower than, say, from the sun, about kilobits per second. So it actually took us a few weeks to download each and every one of those images of the touchdown at Mars after the event actually happened, so we could post it up on YouTube in a high definition manner for everyone to enjoy. One, for the latency, and two, because of the rate of communications decreases. And I'll talk more about why that is in a bit. But once we got settled in on the surface of Mars with Curiosity, this was one of the first pictures that we took. And this is a very high resolution picture. These pictures are many gigabytes large. It's actually a mosaic of many smaller images that were exposed and stitched together. So imagine how big one of your thumb drives is. Maybe you got a 32 or a 64 gigabyte thumb drive. You could fit one or two of these pictures on that, and it would fill it out. It's an amazing picture because you can just keep zooming in and in and in, and planetary scientists and geologists can make scientific observations from the image. But that image it took about 32 kilobits per second of effort to translate back to Earth. And by the way, we only talk to our rover about once a day for about 45 minutes. So it takes many days to transmit an image like this back to Earth. And of course, video, which is nothing more than a composite of many images, takes that much longer. A quick question here, which was, are solar flare events harmful to the rovers? Absolutely. So we have to develop radiation-hardened or radiation-tolerant hardware in the processing, so the actual CPUs, as well as the memory that we use to store. So like a flash drive, like I referred to, typically has NAND-based flash. It's a flash memory device that doesn't do well in the radiation environment. So we have to spin off other technologies that are either inherently robust in that radiation environment, or we encapsulate them in materials which would act like an absorber or a reflector to those materials. And that goes for software as well. So when we're coding up software, we have to think about failure modes. And if you're going to make a decision based upon two inputs, you might code that up 3 different ways and have an arbiter that looks at the best 2 out of 3 within your code, because you know that radiation could come in and one of the gamma rays could flip a bit on one of the inputs and change the state of the output. So very good question. Thank you. Thank you for that. Very timely. Okay. All right, going a little further out was a more recent mission, was our Juno mission to Jupiter, and I hope everyone has seen images of Jupiter, and more importantly, some of the videos of the red storm on Jupiter, which is, we estimate about 1,000 years old. The storm itself is larger than the Earth itself, but a more recent video of Jupiter was released from our Juno spacecraft, which has a camera on board. I'll play that for you right now, which is just amazing in terms of really observing the inner structure of the mixing of the gases. Basically, looking at this, you can see there's no laminar flow. It's all turbulence. It really kind of looks like a painting. We're going across the equator right now of Jupiter, and you can already see some very large storms. Those are the white formations, which as we start to pull out with the spacecraft up towards the North Pole, you'll see that each of these storms exist periodically around the equator. It's just a very interesting formation, so they're almost equidistant from each other all the way around. So this kind of detail, of course, we've had many great ground-based observations of Jupiter. You can see it from your backyard with an amateur telescope. But going out there and observing the structure as close as we can with a robotic spacecraft can reveal so much more about the dynamics of the planet and showing that everything is in constant motion. Juno, as well, is a very interesting mission in that it is a nice example of citizen science, where the public gets to vote on what Juno looks at next. So you get to figure out where the camera is going to be aligned. Moving a little further out, back to Saturn again, the Cassini mission is one of our seminal missions out to that particular planet. and it had a couple interesting components to it. Cassini itself is weaved in and out of the rings. We found moons, shepherd moons, trapped within the rings. We've made great observations in terms of the fact that the rings aren't perfectly concentric. They actually wobble a little bit, as well as they spin. The rings are rotating with the planet. Again, observations that you can only really make when you're very near the planet. Also, there's some interesting activity. If you look on the video that should be queued up right here, up at the North Pole, there's additional storm activity and a very large hexagonal storm right over the North Pole of the planet. Enormous, very sharply geometric storm rotating with the planet that you can see on the cap. And that was very befuddling, making that observation. We've since been able to replicate that using some fluid dynamic modeling, that you can create such an event from a fluid type spherical element that's spinning, but we've never seen anything like that up until that time. So just an interesting revelation. Again, something you couldn't really discern from a ground-based telescope. Another part of Cassini that's less well known is the other part, which was Huygens. So Huygens was you can think of it like a drop zone. It was a robotic element that landed. It was attached to the spacecraft Cassini and then got deployed and landed onto one of its moons, which is Titan. And I have the landing video for you here for that. The video is much longer, so I just clipped out a portion of it. But it's great if you go up on our YouTube site and look at the complete Huygens descent into Titan. You lace through a few mountain ranges, go through a cloud deck, and land on the surface, which I'll show you. But what I wanted to point out about this is the excellent visualization that folks with arts degrees put together to help visualize the telemetry going on during this descent. So everything that you see around the camera, such as the bridle up to the parachute and the RPM that the Huygens descent mechanism is spinning, and all the photonic measurements that are being made, the altimetry. It's a great way to help visualize all that scientific data, which takes a little bit different of a mindset. And so this was I'll play the video here for you now, just a great collaboration between some of the STEM, the technically minded people, and the arts people putting that visualization together. So here you can see Huygens descending into Titan and all the way down to impact. And again, this is just the last few seconds of it. And then you can see some of the rocks on the surface. Then they inlaid some of the lunar pictures on the left just to show you the difference between the rocks on the surface of our moon and rocks on the surface of Saturn's moon. Very recently, we basically finished our journey of our solar system by the New Horizons visit to Pluto. And this was very interesting because it was a fairly low-cost mission that took advantage of some new geometry in terms of the trajectory to make it to Pluto. We're always doing better, figuring out what we can do with gravity assist and flybys of our own sun and other planets to try to slingshot to destinations much more quickly. And then once we got near Pluto, started taking images, and of course did the whole flyby. But being so far away from Earth at the time that was accomplished, it took about a year to transmit all of those images back to Earth for a flyby that only took a couple days, because the rate from Pluto distance back to Earth was about 2 kilobit per second. So even with all the data compression that we can do, the files are still fairly large. They're all high definition. So it takes some time, but this is a very important mission, because prior to New Horizons at Pluto, if you were to walk in the library and look for a book on Pluto, you wouldn't find one because they didn't exist. We knew very little about Pluto. We knew how to find it with a telescope and some basic observations made from Earth, and that was basically it, right? And now you can fill multiple books with information about Pluto just from this one flyby. So can't wait till we can go back there, hopefully land on the planet and learn that much more. The furthest that we've gone in our solar, or beyond, is really beyond our solar system. We've gone truly interstellar with the specifically Voyager 1 mission. So that makes the Voyager 1 spacecraft the furthest human hand-built object from our home planet Earth that we have. And Voyager, if you know where it is and try to look at it with your telescope, you wouldn't be able to observe it visually. But one cool thing that we were able to do is if you were to take several of our largest ground-based radio telescopes out at a place called the VLA, Very Long Baseline Array, which actually, if you ever watched the movie Contact, some of those radio telescopes were featured in that movie with Jodie Foster. That's what she was listening to for signals. We were able to take those radio telescopes and aim them all towards Voyager at the same time and image the radio message coming back from Voyager, all that distance from interstellar space. And if you took all those images and overlaid them on top of each other, you would see the radio energy from Voyager basically whispering at you, telling you what it's observing. And that's what you see in this picture right here. So Voyager has only a 22-watt transmitter. Probably, if you still have any incandescent light bulbs in your house, this is lower than any of those, right? So very, very low power, but we're able to pick up that rhythmic transmission of information from Voyager. We believe we can keep it going for about another 10 years. We can't turn on all the instruments at once, but by duty cycling, turning on a little bit at a time, we can take some science and then perform some communication with Voyager. So monumental event there that we're going to keep going indefinitely. I wanted to mention the Hubble Space Telescope, but in a little different context. I'm assuming everyone here has seen the images from Hubble, and those are certainly important. But from a space communications and navigation standpoint, there was a very interesting experiment performed in 2017 that verified a portion of Einstein's general theory of relativity, that is specifically what's known as gravitational microlensing. So this is looking at the relativity of basically could gravity bend light. And so this was an observational test, an empirical proof to show that that's possible. And the way it was set up is that the navigation system, the pointing system on Hubble, is such that we have very fine guidance control with our space communications system commanding it, that we can get down to 34 nanoradians of pointing capability. And there was an opportunity that arose where we were going to try to observe a particular star in the sky, where in the foreground of that star, in between it and the Hubble Space Telescope, there would be a white dwarf star with a decent, gravitational field. And so, if Einstein was right, we would actually not be able to see the real star position if we aimed the telescope at it. In fact, we calculated what the gravitational lensing should be, and then basically off-pointed Hubble to where the observed star should be, because the light was going to bend around the white dwarf. And so we pointed it to a blank section of the sky, and lo and behold, the star was observed where it doesn't exist because of that gravitational lensing. So obviously, Einstein wasn't around to see such an amazing empirical proof of gravitational lensing, but it was only made possible the fact that we have such a good communication and navigational component with our spacecraft, and we had a physics-based experiment with such a long baseline between the observer and the observed, with the disruptor right in the middle of that. So something that's very hard to do in a lab bench in your physics lab, but something that our spacecraft was able to provide for us. So you might not have heard of that, which is why I'm trying to share it with you here today. Okay, and of course we have other observational telescopes, Kepler being one, or Spitzer. Both of those have the same job here, which is basically to look for what we consider the Goldilocks zone, or potentially habitable planets that are of about the same size of Earth. They appear to have the same chemistry as Earth. They appear to be the same relative distance from their own star at the center of their solar system to potentially support life. And so we've been naming these, a lot of the Kepler planets after the Kepler Space Telescope. And then more recently, Spitzer found an entire system now, which we call TRAPPIST-1, where we have multiple planets, all about the Earth-like composition and Earth-like size, in close orbit around a small dwarf star. So just an entire solar system, only 40 short light years away from Earth, which is a long distance, but in terms of universal length is actually fairly close to the Earth. Okay, so that is scary and interesting at the same time, but here's something that is perhaps a little more ominous. We also use these same telescopes, as well as our radio telescopes, to image all the near-Earth objects. At any given time, we've got hundreds of objects in a temporary moon-like status in orbit around the Earth. I think there's a big one here today that we've been watching very closely. We do use some of our on-orbit telescopes to do that, but we also lean very heavily on the same ground-based radio telescopes that we use for communication with our spacecraft. Those same telescopes can do radar imaging just like they can do communication. And so the Near-Earth Object Survey Program, which you can also download an app for called Asteroid Watch, keeps track of all these objects, and so this catalogs them, tries to assign velocity vectors to them, tries to figure out the mass of these objects. As you can see, the radar capabilities of that particular dish can also look at the pose of the object, so you can get a radar cross-section 1 hour and then kind of take a look at it a few hours later and see if it's tumbling. This is useful for trying to determine trajectories of objects, or if they're potentially going to just burn up in the atmosphere should they reach our atmosphere. So if you want to stay up late at night watching asteroids, you can get access to that information. The good news is, despite having all these objects in close proximity to the Earth, our own moon does a wonderful job of guarding us against those near-Earth objects, either by directly blocking them from the other side of the moon. That's why the other side of the moon is so cratered, or even just simply redirecting them because of the Lagrangian points in motion between Earth and Moon, and with the Moon being in orbit around the Earth. And so as the object gets near, that those Lagrangian point motions can redirect the object so that we have a lot of near misses for the better. Okay, and let me go just a little bit more. I have one more here I wanted to show you with regard to some latest objects here. Going forward, international partnership is a huge part of what we do. And here's just some nice collaborative work that's been done more recently. So we have Japan, JAXA. They had the Hayabusa spacecraft basically intercepting an asteroid, one of these near-Earth objects. We've also landed on a comet with ESA's Rosetta spacecraft, and if you look at the top video, that's what it looks like when you surf on a comet. So that's just a quick clip from the surface of a comet. You can see the dust of the tail of the comet, that's in the foreground, and in the background, all the speckles that you see in the back are the stars. So the comet being fairly far away from the sun, you get a much better view of the stars in the background. But we provide a lot of the navigational support in order to do rendezvous with these types of objects for our other international partners. India more recently has done an amazing job reaching Mars, and we provided some navigational support for them. And Russia provided us with the only color image from the surface of Venus. We've gotten to Venus, but we haven't been able to get color images back, and Russia has, so you're looking at basically the only color image from the surface of that planet. So today, right now, if you take stock of what's going on out in space, we have about 107 spacecraft throughout the solar system currently operational. There's always ones that are being retired and new ones that are coming up in a planning type phase. And we don't have 107 antennas throughout the solar system, so we have to basically hop around and talk to one and then talk to the other. Certainly we communicate with them, but we also get some other types of data called radiometric data. So while we're talking to the spacecraft, we will also determine its position and ranging, basically measuring how long it took to send a message out to the spacecraft and turn around and come back. Through that ranging, we can go one more and correlate things with the Doppler shift of the return signal, and that gives us a spacecraft velocity with respect to Earth. Keep in mind, the spacecraft has no idea where it is, so every time we communicate with it, we're basically telling it, here's where you're at, and here's your distance from Earth, and here's how fast you're going based on our tracking, ranging, and Doppler information. And then every once in a while, we're able to use two ground-based apertures to talk to the spacecraft at the same time, depending upon the rotation of the Earth and the pose of the spacecraft. And we're able to do that. We can take another radiometric measurement called VLBI, Very Long Baseline Interferometry, which can tell us the angle of the spacecraft. That's what we call the pose, the spacecraft angular pose. And we can get that down in nanoradians. That's very important if you're going to try to enter, let's say, the atmosphere of another planet and hit the atmosphere at just the right critical angle, like a rover dropping onto the surface of the planet. So we'll do a lot of VLBI measurements just prior to that type of operation. So these are the navigational components, the important navigational components that we provide, in addition to communication, sending commands out and getting telemetry back. Of course, we do this with a worldwide network through international agreements of many ground-based antennas. There's some cool video games that you can play here on the right, the networking game and the space communication and navigation demo to try your hand at operating and building out those types of networks. But again, we don't have 107 spacecraft, so we have to borrow time on each of these antennas, and each one will get, maybe an hour a day or something like that. There's an interesting link if you look at the resource window for the Deep Space Network, which is a portion of these antennas. And if you go to that link, you can see right now, this second, every spacecraft that the DSN is currently talking to, the uplink communications rate, the downlink communications rate, the range, that type of telemetry. And it's a great way to just learn about the different NASA missions that are out there right now and what they're doing. So each of these ground terminals will have a mission operations center. The one for the DSN that I referred to is called the Spaceflight Operations Facility. If you're ever out in Pasadena, California, this is one portion of JPL that you can go on the public tour, and you can overlook the very mission operations center, which you see right here. It's been in constant operation 24/7 for some 40 years. Of course, we're in COVID situation right now, and so amazingly, for example, the rover that we're driving around the surface of Mars, the folks that operate the SFOF, as we call it, are doing that now from home. So here are the rover operators at home sending commands to and receiving telemetry back from Mars from the comforts of their own home. So it is a brave new window. But in summary, the kinds of things that we're trying to do are to send command and control, tracking telemetry and control. We call that TT&C, and up, and we're getting a lot of the scientific information back. So the TT&C information is typically very simple in nature, very low bandwidth, while what we get back is typically very large, the videos and the pictures. The further that you get, the slower we have to talk to get that information back, and the longer the time will take. For Mars, like I mentioned, it can be 4 to 20 minutes one way. So a two-way conversation with the spacecraft is going to take 8 to about 15 minutes, and it gets worse. It gets into hours when we talk about the Jovian distances and beyond. And of course, if we're talking about human spaceflight, then we have more. We have things like the biometrics, and audio and video become that much more important, and those links have to be very reliable. So we have to do things like encoding for errors that are going to happen. There's always errors in our communication. Typically they're on the order of 10 to the minus 6th to 10 to the minus 8th. We get a bit flipped because of, it could be radiation or any multitude of reasons, but we have to use different types of error correction codes in order to fix those, and sometimes they don't work, and when they don't, we just have to ask for the message to be retransmitted. So we've been talking about RF communications this whole time, which you have to get some authority from the FCC in order to use, and so we have a contingent at NASA that goes to Geneva about 40 weeks out of the year to try to wrestle with all the different countries on getting a particular piece of spectrum for a particular spacecraft for a duration of time. And that spectrum, as you can see on this government chart, is ever getting congested. We're going to higher and higher frequencies because over time we're flying more and more missions. The imagers and remote sensing capabilities are wildly outpacing our ability to communicate that information back to Earth with RF means. And so the next thing coming is optical communications. Optical meaning using a laser beam and in modulating all the information onto the laser beam to send back towards Earth. This can go magnitudes faster in speed, which certainly we need, but also has some other benefits in that we can come up with a payload on the spacecraft which generates or requires less power to operate and could take up less mass. So either of those two important resources could be reallocated to, let's say, more instrumentation or more imaging on the same spacecraft. And that technology will allow us to do things like, like I show here, basically generate a Google map of the Martian surface and transmit that entire map back to Earth within weeks as opposed to years with an RF-based system. So just kind of a real quick overview of the difference between RF and a laser-based optical system is a thought experiment. If you were to imagine a satellite out in geosynchronous orbit, of which we have many, with a typical RF dish on board of about 3 meters in diameter, or let's say 1 meter, I guess I went with 1 meter in this example, pretty typical, and it's going to be radiating an RF beam down to a ground terminal, and I showed Cleveland, Ohio here because that's where I'm from. So you see the Great Lakes region and Lake Erie in the center of this map. The RF pattern that is created by that satellite to communicate down to a ground station, it's going to be about 300 miles in diameter. So as long as we can align that 300-mile wide beam with the ground terminal, we can communicate back to Earth. If that same satellite were to have a laser on board to communicate, we won't have an antenna anymore. What we'd have is a very small telescope. Typically 5 to 10 centimeters would be what we would see on such a spacecraft. So the telescope gets smaller, the entire payload gets smaller, but more importantly, when you look at the spot on the ground, we now have a very small spot, a fraction of a kilometer. And so this is nice because I can put all the energy right where I want it, right at the receiver. In other words, although in the RF case, we were basically spreading all that information out to everyone other than where the antenna was receiving it, so we had to speak very slowly because we're wasting the energy. With the optical, we can collimate the energy to a much finer point on the ground, and so the relationship between the signal to the background noise is much higher. So just like if you imagine an auctioneer with a big booming voice can talk a lot faster than if you were to whisper. And so laser communications allows us to communicate that much more quickly And as well, it's good for private communications because we can keep the beam within the footprint of the ground terminal. Of course, it's very hard to point. So we talk about microradians and even nanoradians in diameter for those widths. And those are hard to wrap your mind around. So I just put a quick little comparison chart in here. With, what is a milliradian, what is a microradian, what is a nanoradian? So if you look at the apparent moon or sun from Earth, those are in the single-digit milliradians in diameter. They're both about the same, in fact. If you never realized that. But when we talk about optical communication beams, those are always in single-digit microradians, which is about the diameter of observing Neptune from Earth. So pretty much a little beyond the visual acuity range, but a very slender collimated laser beam. Pointing is the hardest thing to do. We require both the receiver and the transmitter to both have lasers and co-bore sight on each other through a handshaking arrangement, like you see right here. But there are many different technologies involved in making this happen. So we still have radios, but we call them optical modems. Obviously, there's a laser. Pointing is difficult, so we have some fine pointing mirrors. We might have some coarse pointing mirrors. Eventually, we get to a telescope with some transmit optics to transmit that beam that's been modulated back towards Earth through Earth's atmosphere, and then you have what looks like an astronomical observatory at the other side, picking up the signal and receiving it and decoding it from its modulation. There was a demonstration of this technology a few years ago on a spacecraft that we flew to the moon called LADEE, Lunar Atmospheric Dust Experiment Explorer, I think, Environment Explorer. And we flew a laser-based communication system on board. We used a laser beacon uplink from JPL on the West Coast to find the spacecraft and lock onto it. And from that uplink beacon, we were able to communicate at around, I think it was around 20 megabits per second, which was very good for an uplink speed. And then the downlink rate was 622 megabits per second, way faster than anything else that we'd ever communicated from the moon. In fact, we were able to download all of the data on the entire spacecraft bus within about 5 minutes with the laser. And that was just a technology demonstration, so kind of the first out for the technology. So through that signal, you could have many channels of HD video streaming from the moon all at the same time. Of course, once it's received back at the ground, what we have to do is receive it very delicately, and that had a body-pointed laser. But newer systems that we'll be flying shortly need to have quite an interesting electromechanical device to give us independent pointing of our laser, and that's what you see right here. So this is a prototype of what's known as a Canfield joint. So this will allow us to independently point the laser so that we can always keep the laser trained back on Earth and the imager, let's say, for an orbit around another planet or a moon, at the nadir position. And so we're always data collecting and always communicating at the same time, thereby getting the most efficiency out of both. Alright, let's get to the reception of the information. Back at Earth, inside a cryostat, typically at a couple of degrees Kelvin, we'll have what's known as a single nanowire photon detector. They're just very small wires that detect one of the photons that had entered the telescope, and they're going to heat up as soon as the photon interacts with them, some Joule heating, and we can detect that heating with a calibration circuit, and then we know we've got a photon. When we receive a photon, we know we have some information, and the information basically translates to, this is basically the most predominant modulation that we use. So it's known as pulse position modulation. I'll just steer it through you really quick here, but if you imagine a series of frames that are made up of multiple slots. In this case, I drew it up so that there's 3 bits in a frame. So the first slot is 000. The last one counts all the way up to 111. And if we get a photon detected on the second slot, then we know that will correlate to a 001. And if it was in the third slot, that would be a 010, and so on and so forth. And the frame resets again. And so what this basically means is that we're in this very interesting regime of, on a single photon that we receive at Earth from the laser, we can have multiple bits per photon, which is incredible from an efficiency standpoint. Now I drew this up as an 8-ary pulse position modulation. I mean, we can count from 1 to 8, 3 bits of binary, but we've already built 64-ary systems, and we're working on 128 and 256 right now in the laboratory. So many bits from that image or whatever that information is can be modulated onto a single photon that's received back at the Earth. And the modulation scheme makes that possible, as well as those sensitive cryogenically cooled detectors. Now, stepping way back up away from that, higher level than the physical layer are the protocols that we need, the networking protocols to make all this happen. So we're basically talking with each other right now using TCP/IP right through the internet protocol. Those do not work in space because of the latencies that we talked about. There can be minutes, there can be hours between the sender and the receiver. So the ideas of acknowledgement really don't work. And those links are going to come up and go down every single day, every single hour. So we need a more robust scheme of networking for space networking, and that's been rolled out as a standard called delay tolerant networking, or DTN. This is an open community which any of you who are interested in networking, and specifically space networking, can join and contribute to. And this is what we're using now on all of our future missions at NASA, so that we can communicate in a much more robust manner. Rather than having point-to-point links, we can start communicating through spacecraft in a more mesh network type arrangement. So interesting on the physical layer side, but also some interesting developments on the protocol and standard side of things. So going towards the future, I want to wrap up here just talking about some important missions that will be flying laser communications. In February, we'll be launching a satellite out to GEO that will have 2 laser communication terminals on board called LCRD. I apologize for the acronym, but the Laser Communications Relay Demonstration. And then later we'll be flying a laser up to the International Space Station, which will then talk through LCRD and down to a couple ground terminals on the west coast of the United States as well as Hawaii. Then we can stream video from the ISS. We have about 10 high-definition videos looking at different places on the platform, and I can't wait till we have a YouTube channel and you can just channel surf between any one of those cameras. We will also be flying out on one of the upcoming Artemis missions on Orion, going out to lunar orbit. That will have a laser-based terminal. And then much further out, the metal asteroid Psyche, which is one of our upcoming robotic discovery missions. Fascinating asteroid. The only metal asteroid we're aware of in the entire solar system. Will also use laser-based communication in order to get the data back, and that will be launching in just a couple of years. And of course, the big push from NASA right now is human and robotic exploration out to the moon, which is the Artemis push. It will most certainly be a composite of RF as well as laser-based communications. They both are useful tools and have their own place. So I don't think you'll see laser upsetting RF, but rather being co-located and cohabiting with it. And so what I wanted to end on was just to kind of go back to where we first started going to the moon after the initial precursor robotic missions. One incredible piece of information is the fact that on Apollo 11, which was the first mission that we landed on the surface of the moon, and of course we had Neil Armstrong place our first human footprints on the moon, that very activity was watched live by 93% of Americans, which is an incredible statistic, because I don't think 93% of Americans even own a television set. So everyone seemed to make it to the center of town or the hardware store or some central gathering place in order to watch this. But we were able to broadcast it live through analog means, so that the public could enjoy their space program and the investment in that. Now, the interesting thing was just a few years later, with the departure of Apollo 17, which was the final mission to the moon from the Apollo program, far less people actually watched that, despite the fact that the cameras had gotten so much better. We learned so much more about space communications. So you can see it just from the picture, how much better the picture quality is from that final departure of Apollo 17. But that said, within the agency, that excitement never goes away. So whether you're thinking of the launch and mission control operations back then, or over at Houston at Johnson Space Flight Center, or today with the robotic missions, within the agency, it's just as exciting as it's ever been, and in fact more exciting as we're unlocking more secrets of our universe through these missions. But the most important thing is what happens on the outside, and ourselves as communication technologists, as we venture out in the worlds and continue to do first, it's important that we can share those wins with the public, because it is theirs and your space program after all, and we have to be able to get live video back, even if it's not live. If it's coming from Mars, at least now you'll know why it's 4 to 20 minutes late, even on a laser. But it's important to have that relationship with the citizens. And even if you don't work directly for NASA, there are plenty of ways of collaborating with us on these endeavors. I have several right here, but in particular, and probably of interest to most of you, would be our academic collaborations and internships. We're fortunate to have a well-funded internship program. Just in my area at Glenn alone, we get about 40 to 50 people every summer, and we get more in the springtime and the fall as well. We're broken up into undergraduate and graduate aspects. So undergraduate is USRP, and graduate is GSRP. We even get postdocs and folks in high school as well. So I highly encourage you to take a look at the NASA intern website if you're interested in helping us out. Basically, it looks like a job board. We post activities up there, and you can respond to them. Your interest in helping us accomplish these tasks. We look for not just engineers, by the way, physicists. We had 10 mathematicians this past summer, despite the pandemic and the virtual nature of internships. And we also are always looking for artists as well to help us with our web presence and like some of the visualizations that I shared with you here today. So, and business majors, legal, everything. So that is it. And so thank you very much for your time. And I'd love to answer some questions here. I think we have a lot here. So.
Got a couple there. We've got a couple of questions.
Okay. I'm going to go in reverse here. Could I tell us where to find more information on DTN? So there's actually a spec that's been written called RFC 5050, and it's out there in a public wiki, and you can read through the specification of delay tolerant networking, which is a higher layer protocol, and there's a community that you can join directly from there. There are a couple universities that we've partnered with, mainly University of Albany, the mathematics department, and Ohio University, the computing department down there. But anyone can join and be a part of that. So you can critique the standard, you can critique the implementation, the actual coding of that. You can develop new implementations of it to run on a microcontroller or an FPGA or what have you. But I would start with the RFC 5050 specification. Then that might eventually roll into some sort of an ANSI standard as well. But it hasn't as of yet because it's still a development effort. How big of a learning curve would go from fiber optic communication knowledge to free space optical? Not much. So laser communication involves a lot of moving parts, and I try to hit just several on here, but everything from material science to software development to mechatronics and all in between. We leverage a lot directly from the fiber optic communication era. So I didn't mention this, but we utilize as many of the components from fiber optics as we can, specifically those centered at 1550 nanometer. That's what we're using for space in the West here for our standard. Of course, that's 1550 nanometer plus or minus a few nanometers, so there's some bandwidth associated with that. But all the optics, the fine pointing of that optics, and the sources are all leveraged from the terrestrial telecommunications industry. So if you want to get involved in that aspect of it, you wouldn't have to learn anything. And then the rest of it, there's some excellent books. I would recommend starting with a book. There's two books, both written by Hamid Hamadi of JPL. One of them is on deep space laser communications, and one of them is on near-Earth laser communications, and they're both fantastic. Wonderful representations of the technologies needed for both. So that's where I would get started. Great question. Okay. The question here, optical communications offers the ability to send more data, but is there still a problem with latency for deep space missions? Absolutely. So the latency will be the same with a laser as will be with RF. So even on a human mission to Mars, astronauts communicating with Earth will face long delays. Correct. Absolutely. At a minimum, 8 minutes round trip. So you will not be able to hold a live conversation. Even if you were video conferencing, you would send your message and then go make yourself a cup of tea, come back 8 minutes later and get the response. So this is going to have some large, physiological and psychological effects, thinking about how to stay connected to humanity. Knowing that messages can't be sent faster than the speed of light, what is NASA doing in terms of planning for deep space missions? So there's been several studies done where they try the isolation experiments, and the long-term mental health is one of the many aspects that they're looking into right now. But you are correct. There's no readily available way to build a radio that can have faster than light communications. That said, there is some very low-level research, particularly in the quantum communications regime, trying to figure out how we could potentially build a radio that could send a message faster than light, faster than the speed of light, by looking at some observed phenomenon in nature and figuring out if we can actually engineer that phenomenon. But like I said, that's very low, what we call technology readiness level, a TRL1 type conceptual work. So as of right now, and for the foreseeable future, I would say for the next few decades at least, we will be building radios for RF and optical modems for the laser communications, and we're going to have to deal with these time delays. Yeah. There's many other issues as well. The radiation is a huge one, like I mentioned. I know our Cleveland Clinic right here in Cleveland, we do a lot of research with them on the atrophy, bone density loss, and muscle atrophy, because in a microgravity environment, exercising is futile. Okay. Data encoding.
I think
I'm sorry.
We're a little bit over the hour, so I just thought if you could give us some final thoughts and wrap things up. Lots of questions and so much information, really wonderful. But maybe just some final thoughts.
Sure. Yeah, I'd say going to the future, I did mention we have 107 spacecraft. I would assume that number is easily going to double, if not triple, just within the next few years. And the big reason for that is the fact that we have so much commercialization going on. We have many options from private spacecraft folks giving us rides, and so the amount of missions are going to go up. The space communications and navigation environment is crucial to making all that work. We've got easily hundreds of thousands of people that are associated with it across the globe in some way, and you may find yourself as a part of that community going forward, and I hope that you do, and perhaps our paths will cross. But there's a lot of opportunity there, and I think it's a feather in our cap that NASA doesn't have to be the only people doing it anymore. The fact that we can have commercial entities launching missions, but like I said, it's a very multidisciplinary endeavor. You have to know a little about everything, and you get to work with other people that are from very different areas as well. So it's highly rewarding, and something that you might want to consider as a career. And thank you very much for your kindness and attention here.